Hello everyone, thank you very much for joining me again for another episode on data structures and algorithms. Today we discuss about breadth first search and depth first search with trees, and we're gonna demonstrate, write some code, try to figure out how to implement it. You'll see there are very simple algorithms, and with this occasion we're going to discuss a little bit more also about trees, because in the previous episode we discussed only specific binary trees, if I correctly recall. So now we can dig a little bit more into trees, and with this occasion also discuss about this algorithm. So let me share my screen and start as usual with describing how trees look like. Again, I know we discussed about trees in the previous episode, but remember we only discussed binary trees, where a node, a specific parent node, has only 2 children max. So it might have no children, it might have only one of them, the left or the right, or it might have 2 of them, but 2 is the maximum. So you refer to them as being the right and the left child of a tree. But in the case of generic trees, now you might have multiple children, so you might have actually as many as you want for one node, and it would look like that. Now say you have this one might have 2, and then this one might have 1, and so on and so forth. So you can have as many as you'd like, and now you can create different kinds of trees that look different. No, so you have this is my root, no, and the root here has 1 2 3 4 no children. So this is how it would look like. And of course, normally each of the children represents something. They should contain some needed data, but I will not draw it anymore here, just because I want to save some time. Yeah, so you have it like this, clear? And then this node here has only 2 children. This one and this one have no children. This one only has one child. And then you have three more children for this one. So this is how a generic tree looks like. Okay, and of course the topmost node is called also the root. But just observe, unlike the example we had in the previous video, here you don't necessarily only have two children for one node. You might have as many as you'd like. Okay, so now the question is how we traverse this tree starting from the root. And of course we have multiple possibilities. Now we will discuss about 2 of them, which are called breadth first search and depth first search, and the abbreviation is DFS and BFS, and they refer to which is the direction on which you go first when parsing such a tree. So if you think about this tree as in a coordinate system, you would have a coordinate on the vertical and the coordinate on the horizontal. Now if you want, I can even draw that just to have your imagination stimulated. No, so you can think about it this way. So this is on the vertical is what we call the depth. Oh, sorry for that. So this is depth, and then on the horizontal you have the breadth. Okay, so now of course when you say that is Depth first search, you mean that you always go in first in depth, and then you come back, and then you try to always treat with priority this vertical arrow rather than the horizontal one. While when you say that you traverse the tree on the breadth, then it means that you treat with priority the horizontal and not the vertical. So these are the two main ways in which you can traverse a tree. You either consider as a priority the depth, and then you go on the vertical and you come back, and it's always a priority on the vertical. It's actually also the way in which we traversed the binary trees last time. Or you want to go on the horizontal with the priority, so you always put all the nodes of the children in a queue, making sure that you always traverse them with priority before stepping into the next layer. So it is one of the ways in which you can preview this is considering that each of the generations here is a layer. So you can even call them generations, no? And they say root is the first generation, and then its children are the second generation. And then you have this third generation, and in our case we even have a fourth generation, and so on and so forth. Okay, so you can think it about this, you can think about it that way, so with generations. So what you can say is that in this case you put the accent on making sure that you traversed a generation before proceeding to the next generation. That's how you can see it as well. That's why if you talk about the horizontal traversing, so the breadth first search, web crawlers, for example, are a practical implementation that behind the scenes might use this kind of traversing. And of course, social networks, they sometimes use this behind the scenes as well, because this might be you, and this might be your friends, and then this might be the friends of your friends, and sometimes you have things that you want to do based on how far you are from the origin being the root of the tree. While, for example, when you go in depth, examples can be XML or JSON parsing, where you want to go find out the entire object before going back. So if you want to create an object mapper, for example, I think that's the most used object we use in Java for that. You would have to implement your own depth first search on the tree in this case being the XML or JSON representation of your data. So you see, there are a lot of practical things that you use behind the scenes, these algorithms. That's why, even if, again, you might not end up having to implement this yourself, it's a good thing to know. Now, how do we implement this too? Because I know you love seeing me drawing stuff, but I know that you love even more writing code. Now you want to write Java code for this specific thing. So I think this is DSC6E1, which project, as you already know, you will have available on my GitHub account after this video. By the way, I forgot to mention, but you probably already know, if you are here live with me, you can use the live chat. I already see a hi there. I say hi back. If you want to start discussions or ask questions, the live chat is there for you, and I'm keeping an eye on the live chat. If you watch the event recorded, of course, you can still ask your questions in the comment section, but let's see if I will make a good job in explaining, hopefully, this as good as possible, and maybe I will already be able to answer all your questions in advance. Yeah, I complicated myself probably creating this Maven project, because now it seems to take a lot of time for for it to be loaded, but finally it's over. We don't need any dependencies, we don't need Maven for this, so you can simply create your own plain project for this example. How do I call it? My tree, because I lack of inspiration, you know. And then I will simply create a very simple tree, and then I will define two utilitary methods to demonstrate how to implement the two algorithms that I was trying to describe a little bit earlier with my diagram. Know the possibility to go first in depth or first in breadth. So what do I need? Of course, I need a class node, and for making things simple, I will consider the data as being an integer number, but normally you could have a generic type there. So when you implement a real tree, the generic type would be useful, because you would be able to have any kind of data you'd like on the node. And then of course each node has any children it likes, so I can use for that a list of nodes that I will call the children. So children, okay. And then of course, whenever you create a node, so what I will make sure is that using the constructor, you at least provide the data, and then I would also make sure that this children list is instantiated. And for our simple example, an array list should be more than enough for our needs. Now, of course, the tree itself will start from a root. So I would have a node root to begin with. And then I can simply just create some methods. Normally I should create a method that adds something. Remember, if it's not a binary tree, then you have no constraint on what and how can you add. Remember, when we discussed in the previous lessons about the binary trees, we used them on a specific way. Now you could only have max 2 children of a node, and it was mandatory that the left children to be smaller than its parent, while the right one would be larger. So that's a very important characteristic of the binary search trees, because that's how we use them to put values in a specific order when you add the value to the tree, so that then you can only traverse it to find everything in order. And that's how, for example, a tree set works behind the scenes. We discussed all these details already in the previous episode. I don't want to spend again the time, but normally here you can add you can add to any node, including the root. You can add as many children as you'd like. Okay, so what we could do is, if you want to have things simpler, is you can create some getters or something. Let's see if that's needed at the end, but the idea is that you should allow the addition of an unlimited number of children to any node. Okay, what about traversing? So let's say this is starting with BFS. How do we do that? How do we first take into consideration the generation? Well, normally I will start now with root. What you could do, and maybe it's useful, remember, you can also parse subtrees. So in this case, I will just consider I'm starting with the root of the class, but you could as well, for example, just define this as static and then start with a specific node, because if you'd like to, going back to my example here, if you want to start only with this node, then you should be able maybe to start with this one. So you can this way start with this node of the second generation and only traverse the third and the fourth generations. So if that's what you need, you can do that, and you can implement the your method to allow you to parse a subtree and not necessarily the entire tree. But for the algorithm itself, it will not make any difference. So I can just, in my case, consider the method I implement is for the whole tree that starts with this root here. So then what do you do first? And you first make sure that the node you have as a root is not null. So if it is null, then of course you don't have what to traverse. So you can just simply return, sorry, it's root, not node. Okay. And then if it's not null, then it means you have something, so it will step on the next instruction. So then what you need to do is make sure you use a queue for the children, because if you want to go on the horizontal with priority, then what you need to do is to make sure that you always keep the next generation in a queue, so that you will be able then to go through the queue and take the items one by one to traverse them before you go to the next generation, and so on and so forth. So in this case of ours here, you would define the queue. We can use a linked list. Remember from other discussions we had that linked list is not only a list, but it also implements the queue interface. Okay. So it actually implements the deck, which implements the queue. Okay. But I will use it now as a queue, so I will make an excellent use of the interface segregation principle here, which will allow me to use only the specific characteristic of the contract, which in my case it's a queue. That's everything I need. I just need a queue. So I'm gonna, in the queue, I'm gonna add the root, and then I will say something like that. While the queue is still not empty, it means I haven't ended with all the nodes in the tree. So this queue that I have created, I will constantly add the generations to it, meaning the nodes on the next generation, meaning that you will only end up with it when you have completely parsed the whole tree, which means that I would like to say something like, if the queue is not empty, which I should be able to write it like this. So if I haven't reached the situation where the queue is empty, then I take out from the queue the next node. So I can say var current node is from the queue poll, which will remove the root in this case. And then, because I've parsed it, so here is where I start the parsing, and then I say system out the value of the node. Okay. And then for all its children, go through all of them and add them to the queue. And that's it. Because now, so I parsed the current generation and I added all the children in the next one. So now they will be basically added to the queue and taken from the queue in the exact order I have added them there, because that's what a queue is. A queue is that kind of a structure. I think we discussed also this in one of the first couple of episodes of this playlist, where you use the principle called first in, first out. So you cannot go to the next one until you have taken the one that's already waiting. So what I'm doing here, I'm starting with the root, and then I'm progressively adding to the list all the children, this one, this one, this one, and this one, and so on. And then I will add this one and this one, and so on and so forth. So the idea is that I always put them in the queue, which means that they will always be taken in the order by their generation. And this way I make sure that I will go layer by layer on the horizontal by simply using a queue that ensures the fact that they will be put in a weight and taken in the right order that I want. Starting with this one and then taking this one, this one, this one, and so on and so forth up to the end of the tree. When there is no more node in the queue, so when all of them have been pulled out, then this condition will be true, will be true, and negated, of course, will be false, meaning that it will step over the while, finishing this way the parsing. Okay, by comparison, let's see how we implement a depth first search. Normally, of course, I have to test first that my root is not null, because otherwise I don't have anything to parse. Then what I can do is I print out the data because I have parsed this node, very similar to what I did here, just that I don't enqueue it anyhow. Because the only thing I need to do now is to go through all the children, so it's basically the same thing I did here. But instead of putting them in a queue, I will make sure I will go to each children by itself. And I'm not sure this works anymore with the root this way. So for this one, because an easiest approach is to make it recursive, what I will be forced to do is to do something like that. I will actually change my implementation using a current node, and then the public method, considering to be the one that you would call from outside without the parameters, will simply just call this one from the root. Why? Because I start with the root, but then to make it recursive and allow me to change this now to use the parameter instead, and that will allow me to say DFS C, meaning every time you re-enter the method from the current child out of the list of children. So if I'm going back to my drawing here, imagine in this case what happens is you start with this one, and then which is the root, and then you parse with a for the list of its children, which are these four here. But if you take a look, for each children I call again the method. So what happens for the first is that I parse it and I call the method again, and the same thing will happen. Four of its children will get back, meaning this one will be parsed, and then this one will be parsed, and then it will go back and will parse this one. It has nothing below, so it simply goes to the next, which has nothing below again, so it goes to the next, and then the next, and then the rest until the entire tree has been parsed. But you have seen the difference with this is that being we don't put in a order, in a queue, the children, and we simply just recall the same method recursively, it will simply just always go down below to the next, down below to the next, always the first child to the first leftmost, let's call it, child. And then it will go up, basically focusing on the depth and not on the horizontal, on the breadth. So this is basically how these two parsing algorithms work. Now, Of course, you can test it easily. If you want, you can just add somehow. So in my case here, I should be able to get the children, to be able to add something. So the easiest way would be to give me a way to add the children, and then we can just create a tree like this. Say we have at least a node called root with an initial data. And something to allow me, of course, to get the root. So let's say here, my tree with a route starting from 1. Then I get the root, and let's see what happens here. So it should have a get children, no? What am I doing wrong here? Oh, the class is private. Okay, sorry for that. And then you can add something here, like create some nodes. I will put them before to make things clear. Then I have 3 nodes. And then you can do the same for at least one of those nodes to make your tree a little bit more complex. No? So for example, for N2, you could create 2 more nodes like this. And then you can say children get index 1 means the second, and then add N4 and then 5. And you can test to see 1, 2, 3, 4, 5, and 6, and see what happens. So T, and this would be on the horizontal going. Okay, so what you can see is that it took first the root, and then 2, 3, and 4, and then 5 and 6, because if we are to draw this, what we have now looks like this, no? So I have this 2, here, and all of this will disappear actually. So this is how my tree looks like now. This is the root number 1, and this is 2, 3, 4, 5, and 6. So you can clearly see how they were actually taken on the horizontal. No, it first starts with 1, and then 2, 3, 4, 2, 3, 4, and then 5 and 6. If we change this to the depth first search, now the order is a little bit changed, meaning that the children, being a small tree, is more difficult to see, but it's clearly not 1, 2, 3, 4, 5, 6. Now the 5 and 6 are parsed before 4. Why? Because if you go here and you take it in the depth order, you'll see it's 1, 2, but 2 has nothing below. So that means it goes to the next child, 3, and then it goes to 5, and then it goes to 6 because 5 doesn't have anything below. And then the last one is the 4th. So see the difference between breadth first search that was 1, 2, 3, 4, 5, 6. So this is the breadth first search. And the DFS, where we went 1, 2, 3, 5, 6, 4. 1, 2, 3, 5, 6, and 4 only at the end. The larger the tree is, the more changes, the bigger the difference, of course. So this was a small example. We will not observe too much, but I guess it's more than enough to demonstrate the outputs and the difference between the two ways to parse that, and of course to also demonstrate that our implementation works the way we desired it to work. So a question, and I think if we don't have others, we can close because we finished with everything. Can you explain when would you use DFS versus BFS? Yes, basically there are many algorithms that you could use for each one or the other. But I was saying at the beginning that, for example, web crawlers and social networks are good examples for the breadth first search. The reason is, imagine social networks, and it looks very, it was even in my example now. If this is you, then you have the next are your friends, your direct friends, and then there are the friends of your friends, and so on and so forth. And sometimes algorithms behind the scenes in social networks rely on the distance between you and some specific generation of friends. For example, who does that social network recommend you as your next friend? Most likely your next friend should be one of those who are direct connections of this one. So in order to find that, you use what? A breadth first search algorithm. Another good example, let me see if I find it. I love on Manning, for each book they have implemented this tree here on the right. Where is it? Look at this one. See? So this is a tree. This is the book you are on now. And this is the first family, meaning the books that have been most often bought together with this one. And then is the next one, and then the next one. So this is exactly, is this book, the first preference, the second family of preference, the third family of preference. Again, if you want to create this tree, it's a tree. It's actually a graph, sorry, this one, because you see, you might have links between many, but imagine you wouldn't have had it would have been a tree, but the algorithm is the same. So if you want to implement this way, to make the colors here, you would use a depth first search, because you want to first, you are in the route, and then you want to parse the next family, and then the next family, and then the next family. So exactly like I did here, no? Is the next first family, second family, third family, fourth family, and so on and so forth. Yeah. The same with web crawlers. Web crawlers are tools, let's say, with the capability of parsing web pages and then the web pages associated and so on and so forth. So imagine you have parsed a web page. Let's say you have a website, no? In this website, in this page of this website, you will have links. Some of them will be to internal links, some of them will be external links. So what you want to do is to make sure you always parse everything related before you go more in depth to something else. And you will basically go in depth as much as requested. Usually you have a finite number of pages to which you go in depth, but you first make sure you parse everything that is on that first page before going more in depth, and then you parse again what is on that second page, and so on and so forth when you create a web crawler. So this is another example of a good usage of a breadth first search. While in case of a depth first search, I was saying that a good example is creating a JSON or XML mapper. Like in Java you have, for example, object mapper. I'm pretty sure you have used it. It is a tool that we very often use to transform, for example, from a JSON text into an object. When you have a JSON or an XML representation, like this is a JSON representation, now you have attributes with values, and you know some of these attributes at some point, well, I see this text is not really the most, I'm not sure how to put it. Okay, this is the way. And it's not always a simple attribute. You might have objects as attributes. Well, Draw.io is not the best tool to actually represent JSON, but I'll try my best. No, and you have objects, which they might have objects and other attributes, and so on and so forth. So now, when you try to parse this data, this piece of data here, when you try to parse this piece of data here, you are interested to, first of all, go in depth, because you cannot create object C unless you have determined what D is, no? So you cannot finish the creation of C until you have parsed everything that's inside. So then what you do is you parse this tree in depth so that you reach the final object, the ultimate object, you create that one, and then you would be able to create the earlier one, and then the earlier one, and then the earlier one. So these are good examples of using BFS and DFS. Of course, you have to think about what you need exactly. Are you in a situation where you cannot interpret correctly 2 unless you have already discovered all of its children? If that's the case, you will go in depth, like XML and JSON parsing. While if what you need is to see the family, the whole family of the children, or to analyze it by family or by layer, then what you do is focus on the horizontal, so on the breadth. Many algorithms need either one or the other. Depending on what your case is, you will figure out you need a depth parsing or a breadth one. Okay, so I hope this clarifies everything. I hope you've learned, and I was good enough to not only demonstrate you how to write the code, but also to explain you how these parsings work and when you need them. And that concludes our discussion for today. Thank you very much for being here with me and for asking your questions, of course. And remember, if you still have questions or if you maybe couldn't be here with us today, you can always use the comment section. Follow me also on Twitter, X, or whatever the name is now, and LinkedIn. And keep in touch. Until next time we meet, I'm waving goodbye and saying have an excellent time.